So we went over how to delete something from the tree if you've got no children. We just simply remove it and we do that by telling our parents, hey, set whatever I am to null instead of me. Okay. What about removing something like 3 where we have 1 child? Well, let's think about how to handle this. Well, we've got 3 over here, and we can't just simply tell 5, replace me with null, because if that was the case, we'd lose 2 as well. Right? If I told it to replace, if 3 told, hey, if we're deleting 3 and 3 just simply said to 5, hey, replace your left subtree with null, we go, okay, and then we lose 2 as well. We don't want that. So, but if what we did was simply say, hey, I've got a child, why don't you adopt that child? 5 will go, hey, that sounds like a great plan, and we can just simply, and we'll keep everything in order, right? So if you've got 1 child, all you do is you ask the grandparent of that child to adopt it. So in this case, if we deleted 3 from the tree, we essentially promote 2 to being 5's child. So here we have 2 separate cases. Case 2, root has only left child, and the third case is root has only a right child. So if root dot left is not equal to null, but root dot right is equal to null, then what are we going to do? We are going to instead return root dot left. Here we're telling the person who called me, hey, replace me with my left subtree, right? And that will maintain, and that will be keep in order, right? Because I have only 1 child, right? Doesn't really matter. So let's go ahead and put 3 back over here. And then I'm going to use a new symbol over here, which is I'm going to use a triangle symbol over here, which simply says this is a subtree of indeterminate size. Okay? We know that basically everything in this subtree of an indeterminate size, there could be like millions of items in this subtree, but we know because this subtree is the left subtree of 3, that everything in here is also less than 5. So there's no problem in just attaching it to and making it 5's left subtree, because everything, if it's less than 3, then it's got to be less than 5. So that's what we do. We delete here. And then we make this the left subtree. Awesome. So that makes sense. And then it just makes sense for if we were deleting something that's the right subtree as well. So say, let's go ahead and go back to brushing, select, let's clean this up a bit. So say we've got the same tree over here, we've got 8, and then we've got 9 over here, right? Say we want to delete 8 again, right? All we'll do is that we'll make 9 7's right subtree. And we do that by just simply returning root dot right in that case. Or say that 9 is again a subtree of indeterminate size. We know that everything in this subtree has to be bigger than 7 because it's greater than 7 and it's greater than 8. Otherwise, it would have ended up somewhere else. So, so we now make that indeterminate subtree the right subchild. In this case, case 2, or case 3, we just simply copy this, but instead of doing root dot right is not equal to, actually let's say just root dot left is double equal to null. Root dot right is not equal to null. So that's pretty good. So that's, oh, and here. Okay, so now here's the question. How in the world do I, sorry, let's go ahead and, I like having a nice big undo operation. Okay, except here's my really badly drawn 8. Let's go ahead and actually, I probably should make a new tree for this because just simply to show you how deleting something like 5 would work. So 5, 12, 15, 14. Yep, there's going to be a big tree here. 14, 7, 3. Let's actually make that a 1, a 2, a 3, a 0, and we'll put a tree of indeterminate size there. Okay, we'll put another tree of indeterminate size. Actually, let's not make it overly complicated. We'll go ahead and keep out those trees of indeterminate size for right now, just to make sure that everything. Khan Academy, I am not. Maybe I'd do better with a Wacom tablet, but okay. So we've got, so now let's go ahead and look at what we've learned how to do. Deleting 3 was fairly easy. Deleting 14 and 20 were fairly easy because they're leaves. If we wanted to delete 2, we now know that we would just simply make 3 the child of 1 in this case. Okay? But say we wanted to delete something with 5. What the heck do we do? Right? We kind of just have to replace this root, right? We can't just delete 5. And so let's just try a few things. Okay, if I delete 5, can I make 12 the root? Well, that wouldn't work because we'd then we can't just promote 12 like that because what the heck do we do with 7? Do we have to like toss it onto the end of 3? Because that would keep things complicated. That would make things really complicated having to do that operation, then throw 7 over to there and have 3 catch 7, right? And we can't just keep 7 where it is with 12 because 12 is bigger than 7. So 7 has to move to the left. That makes things complicated. You can't just replace it with 1, by the way, either, right? You can't just like replace it with your children. Neither of your children really make it easy to replace you because again, 1, we make 1 root, then we'd have to move 2 and 3 over here, and that looks like a mess. Not just 1, but 2 and 3. I mean, we put that, so what? That'd be putting 2 and 3 over here by 7. That seems like a whole lot of work. All right, what about 0? Can't really make, while 0 and 14 and 20 have this great attribute of that they have no children to take care of, right? They have no children to take care of. Putting 0 here, right? We'd have to move everything over to the left. Sorry, we'd have to move everything over because everything's bigger than 0. We'd have to, if we put 14 here, 12 and 14 wouldn't really fit. Same with 20, 7, the 12, and the 15 won't really work out. But if we look at replacing 5 with 7 or with 3, then actually it's actually quite interesting. If we replace 5 with 3, then everything just works out, right? There's no need to move anything around other than the 3, right? 3 is less, it will basically be in the right place because everything in the left subtree its left subtree 1, 0, and 2 will be smaller than it, and everything that was bigger in it will stay in the bigger side. We went ahead and replaced 5 with 7 instead, right? Replaced 5 with 7 instead. Then that actually also works out because replace 5 with a better drawn 7. Okay, that's going to work out too because we took this and everything, you know, that 12 is bigger than 7, and it's bigger than all the stuff in the left subtree because 7 was already in the right subtree, so it was already bigger than the root. But what's so special about 7 and 3? What made them so special? Well, think about, I'll give you a bit to think about it. Pause the video and think about what makes them so special. And wait for you to come back. Well, pause it. And welcome back. I hope that was more than a couple of seconds for you. So what makes these two guys so special is that, if you notice, 3 is the biggest thing in the left subtree, and 7 is the smallest thing in the right subtree. If we basically were to do an in-order traversal of this tree, we'd go 0, 1, 2, 3, 5, 7, 12, 14, 15, 20, right? So 3 and 7 happen to be things that are right next to the root, and we can replace it with either of them. And the things that are right next to the root in an in-order traversal turn out to be either the biggest thing in the left subtree and the smallest thing in the right subtree, right? It actually is amazingly simple to. So how do we find these things? Okay, now that we know that we can replace it with what's called the in-order predecessor, the thing that comes before you if you do an in-order traversal, or an in-order successor, the thing that comes after you do an in-order traversal. How do you find these things? That sounds really complicated. It's actually one of the easiest things we have to things to describe. It's slightly harder to code, but it's really easy to describe. To find your next in-order successor, to find the biggest thing, the biggest thing that's smaller than you. In-order predecessor, the biggest thing that's smaller than you. We go one step to the left, and then you go all the way as far as possible to the right. So you step into your left subtree, right, because that's all the things that are smaller than you, and the biggest thing in there will be all the way to the right. Why will it be all the way to the right? Well, because if it was to the left, it would be smaller than something in the tree. If we had to go left somewhere, it would be smaller than something. And if we could go right one more, then that thing is bigger than me, so that thing would be bigger. So it's one to the left, all the way to the right. To find the smallest thing that is bigger than me, I go one to the right, where all the things are bigger than me, and all as far as I can to the left. Okay, what if I didn't have 7, though? What would it be then? Well, same rule applies. I go one step to the right, and as far as I can to the left, which happens to be 12. So I'd be replacing 5 with 12, right? I'm going to replace, if I have 2 children, I'm going to replace myself with my next in-order predecessor or my next in-order successor. I'm going to be doing my next in-order successor. Okay, so we'll cover that in the next video.